Today we're going to talk about exponential and logarithmic functions. Exponential functions are some of the most important functions in the real world. They appear in many places, including population, money, with interest and debt, radioactive decay, spread of disease, etc. In addition, the SAT will include several questions that require the understanding of exponential functions. So this is going to give some key characteristics of exponential functions. So an exponential function has a general form of f of x or y equals ab to the power x, where b is greater than 0, and a and b are constants with a not equal to 0 and b not equal to 1. Why can't a be 0? Because then we would just have y equals 0, and if b was 1, then you'd have a horizontal line at 1. So a represents the initial amount, and b represents the growth slash decay factor. And we'll talk about this more later, but b is equal to 1 plus the rate. So we have exponential growth and exponential decay on our graphs right here. Also remember that our exponential graphs do have asymptotes. So this has a horizontal asymptote at y equals 0. And whenever you're graphing your graphs, you should always include your asymptote on your graph as well. So for this one, this is exponential decay when your b value is in between 0 and 1. So increasing versus decreasing. So exponential functions are always either increasing or always decreasing. They will never switch from one to the other. So they have no relative extrema. So remember, that's the local max, local mins. So concave up versus concave down. Exponential functions are always concave up or always concave down. They will never switch concavity, so they have no points of inflection. For our end behavior for exponential functions in general form, as the input values x increase or decrease without bound, the output values y will increase or decrease without bound, or they're going to be approaching 0. So we have these limit statements right here of the possibilities of what it could be equal to. So we have just ab to the x as our general equation for our limit. So it can either go to be infinity, negative infinity, or 0. So let's go ahead and write limit statements for the end behavior of the following exponential functions. So the left limit means as x is going towards negative infinity, what is our function doing? So this is exponential growth. You can see as your y values go from left to right in your graph, they're increasing. So this left side of my graph we can see is approaching that horizontal asymptote at y equals 0. So this is approaching 0. And as we're going towards positive infinity, our values are increasing towards infinity. For the next one, this graph is also increasing. So it is from left to right growing. For this one, we can see that the limit as x approaches negative infinity for the function is going down now towards negative infinity. And over here, the right limit as x approaches positive infinity for the function is going towards the asymptote at 0. Over here, we are, instead of giving the graph, we're given the equation for the function. So you can see that your b value is in between 0 and 1, which means this is decay, exponential decay for our graph. So just a real quick sketch of a decay graph would look like this. So the limit as x approaches negative infinity is going up towards positive infinity, and the limit as x approaches positive infinity is approaching the horizontal asymptote at 0. So that would be for our end behavior. So now we're going to look at also increasing, decreasing, and concavity. So remember, when the curve bends upwards, this is concave up. When the curve bends downwards, this is concave down. So here we can see the curve is bending upward, so this is concave up. And we can see from left to right on our graph, what are our y values doing? They are decreasing. Over here, this is concave down because the curve's bending downwards. And we can see from left to right what are our values on our graph doing. They are decreasing as we move, so concave down and decreasing. And for this one, again, the b value is 4, and the b value in this case is bigger than 0, which means this is growth. So exponential growth, just a real quick sketch of the graph looks like this. So this would be concave up. And as we move from left to right, our y values are, in this case, increasing. So the properties of exponents that you learned in algebra can also be used to manipulate / rearrange exponential functions. So we've talked about the product property before. If you have something with the same base being multiplied, you add the exponents. Power property, if you have a power of a power, you multiply the exponents. And if we have a negative exponent, then remember then if it's a numerator, it goes to denominator and vice versa. So those are some examples below to help us with our properties. So the same exponent rules can be used when working with horizontal transformations for exponential functions. So let's go ahead and look at each of these functions and determine our transformations. So here, notice that this is x plus 2. So remember our general equation for our function, let's say g of x is equal to a times whatever the base may be. So I'm just going to write BASE for base to the power of b times x minus h and plus k. So that's the general equation. And so the base will always stay the base in the equation, but all the rest are just going to be your transformation. So here, this is our h value. So that means to get plus 2, h has to be negative 2, which means that our graph of y equals 4 to the x would be the parent graph, is shifted to the left 4 units. Looking at question B here, this is then a B value is equal to 3. So remember that horizontal stretching compressing is opposite thinking. So that means y equals, and our parent graph, in this case, since the base is 2, would be 2 to the x, which is the parent graph, is shifted, or shifted, sorry, is it's dilation, so is a horizontal compression, or you can say dilation, by 1/3. So looking at C then, our B value, because this is x divided by 2, would be 1/2. So the parent graph, the base is 9, so y equals 9 to the power of x is the parent graph, is horizontally stretched by a factor of 2, because remember it's 1 over the absolute value of 1 over b, so it's a dilation of 2. And then for this last one, the base is 5, so y equals 5 to the x is the parent graph, and we can see that this is an h value equal to 1. So y equals 5 to x, the parent graph is shifted right 1 unit. So now let's re-examine the exponential function from example 1a. And see if we can use our exponent properties to rearrange the function so it's in an equivalent form. So we can use what's called the product property in reversed to show that 4 to the x plus 2 is the same thing as 4 to the x power times 4 to the 2, because you multiply something with the same base, you add the exponents. And then you can simplify that because 4 squared is equal to that 16. So you would get 16 times 4 to the x. So that means that f of x equals 4 to the x plus 2 is equivalent to writing f of x equals 16 to the 16 times 4 to the power of x. So that means if you were to graph these, you'd get the exact same graph. So it says when we rewrite the exponential function this way, there's no longer a horizontal translation, but now we have a vertical dilation by a factor of 16. So that would be a vertical stretch by a factor of 16. So the important idea, every horizontal translation of an exponential function is equivalent to a vertical dilation or of the exponential function. So it could be a vertical stretch or vertical compression. So of f of x equals ab to the x, where a is equal to b to the h. And that's because b to the x times b to the h, so that a value is from the b to the h because it's just going to be some quantity, some number. So each of the following exponential functions has a horizontal translation. For each, write an equivalent representation that has a vertical dilation and no horizontal translation. So we're basically just writing this as a times b to the x. So notice that we're basically saying, how can we get x by itself with the base? So looking at 2, I see this as a plus here, so we're going to use that product property. So again, the product property, a to the power of b times a to the power of c is a to the b plus c idea. So this would be 2 to the x times 2 to the third. And so 2 to the third is equal to 8. So if we rewrite this in the form, we would have y equals 8 times 2 to the power of x, or you could write y equals 8 and then parentheses 2 to the power of x, same thing. So y equals a times b to the x power. So here g of x, same thing. So we have 3 to the x times 3 to the negative 2. So remember, 3 to the negative 2 power is really 1 over 3 squared times 3 to the x. So we get y is equal to 1/9 times 3 to the power of x. So for the, going back to the first one, this would be moving our graph to the left 3. So then the vertical stretch by a factor of 8 would give us the same graph. Here, moving to the right 2 for a base of 3 would be the same thing as a vertical compression by 1/9. And over here we have, so this would be 4 is already there, so 4 times 3 to the x times 3 squared. So then 3 squared is 9, 9 times 4, so 9 times 4 times 3 to the x. So y equals 36 times 3 to the power of x. So that means for this one, we would be changing that to become a vertical stretch by 36. So we're going to talk then next about solving exponential equations by equating the exponents. So we have a property of equality if b to the y equals b to the x, if and only if x equals y. Sometimes it's also called the one-to-one property. So it says solve each exponential equation for x. We've done these before. A, you can see, has the same base. So we just set the exponents equal and solve. So 2x plus 3 equals 4x minus 5. So then when we solve for x, we get x is equal to 4. And these are easy to check your answer to plug in for x. So the domain of an exponential function is all real numbers. So whatever you plug in should work. If it doesn't, then I would look at your work that you did algebraically to see if you did something wrong. Over here, so we don't have the same base. We have base 4 and base 16, but we want to make them the same. So be careful because oftentimes I see kids do this. So 4 squared we know equals 16. And so then they'll write 4 squared here. But you have to be careful because 4 squared does not equal 4. So we can't actually take this 4 out and write 4 squared so that then this becomes 16 to make the bases the same, because again, you have to keep the equation the same. So what would work instead is by taking out this 16, because 4 squared equals 16, we can replace this 16 here. So 4 to the 3x plus 5 equals 4 squared to the 2x plus 1. And then we're going to use our power property to multiply the exponents. So this is 4 to the 4x plus 2. Now that we have the same base, we can drop the bases and set the exponents equal using that property of equality. And when we combine our like terms, I'm sorry, that was plus 2 there, so it should have been minus 2. So if we combine our like terms, we get 3 is equal to x. And again, if you were to plug this in to check your work on both sides, you would see both sides would equal each other. So another important concept that we're going to talk about for inverses. So every operation has exactly one inverse or opposite operation. We learn inverse operations because these will allow us to solve equations involving various operations. So the inverse operation for addition, of course, is subtraction. For multiplication is division. If we have to solve for x here, we would have to take the cube root of both sides. So the question is, what happens if I'm trying to solve for x that's a variable? So this is called, the operation is called exponentiation. So we would like to solve equations involving exponential functions, which creates the need of an inverse operation related to exponentiation. We are not changing the problem when we convert back and forth. We are simply rewriting the equation in an equivalent form. So last year in Math 3, we learned exponential functions and logarithmic functions are inverses of each other. So in order to solve that equation above, we would have to use logarithms. So this is just the fancy definition of a logarithm. So for a logarithm, your base, which is this a value here, it has to be positive, so bigger, greater than 0, but it also can't equal 1. And our x value that we're taking the log of has to be greater than 0. So if that's true, then the logarithmic function y equals log base a of x is equivalent to a to the y equals x. So when written in logarithmic form, x is called the argument of the log, and y is the logarithm, or we say the exponent. So it's important to understand that the logarithm is an exponent. So the answer to the log is an exponent, which we talked about a lot last year. So we learned to convert from one form to the other and vice versa using equivalent statements below. So here we have b to the power of e equals a. So rewriting that in logarithmic form, log base b of a equals e. So again, these are equivalent statements to go from one form to the other. As we said up here, we are simply rewriting the equation in an equivalent form. We're not actually changing the problem when we're converting back and forth. And so again, this is for any positive base b where b is not equal to 1 and a is greater than 0. So notation, if the base of the log expression is 10, remember this is called a common logarithm and it's written without the base. For example, log of 3 is understood to have a base of 10. So log of 3 is the same thing as log base 10 of 3. We also talked about natural logarithms last year. So the logarithm with base e is called a natural logarithm. So log base e of x equals the natural log of x is another way to write it. We just don't write the base. So here the base is e. It's kind of like when we don't write base 10. So the next questions say to convert the following equations from exponential form to logarithmic form. So looking at the first one, we have 3 squared equals 9. So in logarithmic form, this would be the log base 3 of 9 equals 2. And again, because the answer to a log is an exponent. Here, this would be the log base 10 because the base stays the base. But again, we don't normally write that base 10. I'm going to write it here, then I'll write it the other way. So log base 10 of y equals x because the answer to log is exponent. So the other way you can write this would be the log of y equals x. Looking at the next one, we have the base is r and t is the exponent. So the log of r of w equals the exponent t. So that would say log base r of w equals t, and the argument here would be w. Over here for the next one, we have the base is e, so you can write log base e of y equals the exponent 3x. And again, we don't often write log base e. Instead, we use the natural log. So this can be written as the natural log of y equals 3x. Example 2, we're converting the equations from logarithmic form to exponential form. So for this first one, The base stays the base, so 7. The 2 is the exponent, so 7 squared equals x. Here, 3, the answer to log's exponent, so 3x equals y. For this one, the base is not written, so it's base 10. So 10 squared equals y. And over here, if the base is not written for ln, it's base e, so e to the fourth equals c. So evaluating expressions involving logarithms. Sometimes we can evaluate log expressions without the use of a calculator by using its equivalent exponential form. So here we're going to evaluate these expressions without our calculator using that equivalent form. So here we're trying to figure out what is this equal to. So 2 to what power equals 8? Well, we know 2 to the third power is 8. So this would be 3. And you can also get a common base. So we know 2 to what power equals 2 to the third. So then, of course, question mark has to equal 3. So 5 to what power, I'm just going to use x in this case, equals 25. Well, we know 25 is the same thing as 5 squared. So 5 to what power equals 5 squared. So then, of course, if you have the same base, the exponents have to be equal. So that means this is 2. 2 to what power is 32? 5. Again, this is the base 10 if it's not written. So 10 to what power equals 100? 2. Next, I would pause the video so you can do the rest on your own and then pause it when you're done to check your work. So here we have 16 to what power equals 4. So notice that this number is less. So let's go ahead and think about it like this. 4 to what power is 16? So we know 4 squared. So 4 squared equals 4. So this is where we're getting the same base that we can solve. So then remember multiplying these powers, it's power rule. So 4 to the 2x equals 4. And this is to the first power, just don't write it. Once you have the same base, you can set the exponents equal. So 2x equals 1. So x equals 1/2. And that makes sense because if we took the square root, because remember 16 to 1/2 power is the same thing as square root, the square root of 16 is 4. For the next one, we have 3 to what power equals 1. So remember that this would have to then be the 0 power. Here, this is base 10 when it's not written. So 10 to what power equals 10. So that's 1. Here we have 6 to what power equals 1 over 36. So remember, to get a fraction, we have to have a negative exponent. So 6 to what power equals, and 6 squared is 36, but to get it in the denominator, it would have to be negative. So that means this equals -2. 6 to what power equals 6? 0. 10 to what power equals, 6 to what power equals, it's not 0 over here, 1. 10 to what power equals 1? This is 0. Sorry, I was just thinking about the next problem. So 6 to the first equals 6. And then over here, 10 to what power equals the cube root of 10. So we can write this as a rational fraction. So this would be 10 to the 1/3 power. So this is 1/3. And then 125 to what power equals 5. So remember that 125 is the same thing as 5 to the third. So that times x would be 5 to the 3x equals 5 to the first power. So 3x equals 1. So x equals 1/3. And then it says use a calculator to evaluate the following expressions, include at least 4 decimal places after the point. So let me get my calculator. All right, so looking at these next ones, if we want to evaluate using our calculator, remember there's a log button next to 7. So if this is base 10, we can use this button here because that uses base 10. So log of 7, enter, gives us 0.845, and that's 0.9, so 1. And then over here, this is not a base of 10. So we can solve this by doing two different things. We can use the change of base formula. So if I have the log base 7 of 135, if you remember from last year, the change of base formula means we would do the log of 135 over the log of 7. This uses base 10 so that we can solve this. So this would be the log of 135, close parentheses, divided by the log of 7. Always make sure to close those parentheses, otherwise you get a different value. So that equals 2.5208. Another way you can solve this if you have the button, but not all the calculators do, most of the newer ones do now. So if you go to math, and you scroll all the way down, you see A says log base. So if you're lucky enough to have this, it makes it even easier. So log base 7 of 135. But we still need to know the change of base formula. They do use those on SAT and ACT. So again, but notice you get the same answer. For the next two, we are using natural log. So in your calculator, below the log button is the ln or natural log button. So the natural log of 1.3 gives us 0.2624. And the natural log of e, so remember how to get e in your calculator. You can either do second and the division symbol, see that e right there, or you can hit second ln. Those are two different ways to get e. So that would be equal to 1, which makes sense because this is saying e to what power equals e. Well, e to the first equals e, and that's actually a property. And that is all for exponential functions and an introduction to our logarithmic functions with going back from one form to the other. So remember, the important thing to remember is that exponential functions and logarithmic functions are inverses and that the answer to a log is an exponent.